Lecture 12, Part 3. In first two parts of this lecture, we looked at capital energy trade-off, and we said that the value of delta T min is a parameter that dictate the energy targets and area targets of the system. And if the delta T min is lower, we can recover much more heat from the process, and we have less external energy requirement or utility requirements. But if the value of delta T min is higher, we have less process-to-process recovery, and then we have much more higher energy requirements of the process. Another thing is that the value of delta T min also affect the area calculation or the area of heat exchangers. So if the value of delta T min is small or lower, you have low energy targets, but you have high energy area targets. It means that you have much more area required for the desired heat transfer. But if you increase the value of delta T min, you reduce your area requirement, but you have much higher energy targets. Okay, so when we are designing HAN networks, we are always looking at an optimal value of delta T min where we can balance the area target and the energy targets. And obviously, when we are looking at area alone, we are just looking at the area required for heat exchangers or area required for the heat load of the process. But if you look into more detail of the area, we can see that it translates in terms of the number of heat exchangers or number of units, and we can even further break it down into number of shells. And if you look at all these details in terms of different number of units and different number of shells, that gives you much more better understanding of how the capital cost is changing with delta T min. Okay, and if you remember from the previous parts that we saw that the capital cost was much more smoother function of delta T min, but in reality the cost is actually increasing or decreasing depending on the number of shells and number of cubes that gives you this particular area target. So we always looking for optimum value of delta T min, and we are trying to balance our total energy cost in terms of our capital cost that is decreasing with increase in delta T min, while the energy cost is increasing with delta T min. And when we are designing our plant or our chemical production process, we design the process for a certain lifetime. Let's say it's for 25 to 30 years. So we always consider these parameters to calculate what is the rate of return or rate of investment that you will have, because you need to get this money from a bank, for example, and they want to see all these plans and estimates. Also, you do, for example, sensitivity analysis and inflation analysis to see what is the likelihood of changing the cost of energy over that period. For example, is there a possibility to having, for example, a renewable energy, or if you have to stay and use the fossil fuels. So you predict all these things, and then based on all these estimates, you select an optimum value of delta T min. So this is your normal MER HAN design, focusing on the maximum recovery of heat between the hot streams and the cold streams. So by looking at an optimum value of delta T min and with the target of energy recovery, we can see that we can minimize our hot utility requirement and our cold utility requirement. But that also means that the heat exchanger areas in this situation or with energy target might be quite large, because our delta T min is selected based on to reduce the energy cost, not the area of the process. Okay, so there might be situations where you deliberately want to design your HAN network not based on your energy recovery, but actually on your area targets. Okay, so you can have multiple HAN designs based on what target you are looking at. For example, you can be looking at energy target, you can be looking at area target, and you can be looking at the overall cost targets. So let's say if you are looking at overall cost target, it means that your process is designed at a suboptimal level in terms of energy recovery. So whatever the situation is, you are always looking to further optimize this HEN network. Okay, and one way of further optimization is to look if we can still recover some heat between this HEN network. So if we have an MER based HEN network, or a HEN network based on some other target that would not be optimal in terms of energy recovery, so how we can optimize that system? So one way is to look at what are the possible heat recovery opportunities and how we can shift heat duties within a loop. Okay, so what is a loop? A loop is essentially a pathway that starts, let's say, from a particular unit, and then you move around different units, and then it comes back to the same unit. Okay, so that kind of arrangement is what we call a loop. And then we can recover heat between these loops, or we can shift heat between different units of this loop. So let's say if we are trying to recover 60 megawatt of heat uh, around this loop, so we can shift the heat duty around. So here we can recover, let's say, 40 megawatts here, and we can recover 20 megawatts here, or we can recover 30 megawatts here and 30 megawatts here. So we can shift these energies requirements or energy duty within a loop. And because each of these units within this loop will have different values of temperatures available and different values of heat duties available, so they will have different size. And if you move the duties from one exchanger to the other exchanger, you can actually control the size of that exchanger within this particular loop. And we move this heat duty from one unit to another unit in such a way that we minimize the overall area required for this entire loop. So here there is another example of another loop. So here, for example, we are starting at unit A, and then we are going to another unit A, C, C, D, D, B, and B, and then finally we finish at A. So the reason we are calling it a loop, because we started at A and then we finished at A. So we are in a closed loop. And within this closed loop, we can shift the duties around from one exchanger to the other exchanger in a horizontal system, and we can also exchange heat in a vertical system. And again, the goal is to reduce the areas of these exchangers by having, for example, maximum energy recovery. So another way to optimize our design, our suboptimal HEN design, is to look at utility path. And the utility path is a way of connecting different units in a HEN design. So here, for example, we have a utility path starting at hot utility, connecting different exchangers in the process, and then going all the way to the cold utility. Okay, and because we said that we are now in a system that is suboptimal in terms of energy recovery, and we are trying to optimize our, for example, energy, but we are also trying to reduce our area of these exchangers. And again, along this utility path, we can actually shift the heat load between different units. And by doing that, we can actually play with the area of these heat exchangers. Okay, so when, for example, if we are shifting some duty from exchanger A to exchanger B, because we have exchanged the duties, we can have different areas now. But at the same time, because we are changing duties, we are also changing the temperatures available in the design of this heat exchanger, and that again is going to play a role in terms of the area calculation of these exchangers. And along this utility pathway, we shift heat duties between different units with the goal of reducing the size of the heat exchangers. And here there are some other examples of utility paths. So this is, for example, the one that I showed you in the previous style, going from hot utility all the way to cold utility. And then you can have other examples here, like for example, here again, we are connecting these two units. Then we are connecting A, B, and B, and then without breaking the path, we are going all the way to cold utility again. Okay. And if you see that here again, the thing that we are trying here is to shift the load between different heat exchangers, and by shifting the load, we can actually play with the temperatures available, and we can change the size of these heat exchangers. Here there is in, for example, figure C, you have another path that is again going from hot utility to the cold utility. So if it is just connecting, for example, two units, we just call it a path. But if it is connecting a utility, hot utility to the cold utility, we call it a utility path. The goal is to shift the heat duties and then change the temperatures, and as such minimize the area or the overall area of all these exchangers in this utility path. So what we are trying to optimize is the values of these different heat duties along either a utility loop or a pathway or just a utility path. So by optimizing or by shifting this heat loads between different units along a utility path or in a loop, we can actually minimize our overall area of that system. And this is actually a multi-variable optimization problem. You might have discussed these systems in your course in optimization, where we are looking at several variables at the same time with a final goal of minimizing the area of the system. So we discuss different degrees of freedom for example, in the form of either a loop or in the form of a utility pathway to shift the load between different units and then achieve the final goal of minimizing the area of the heat exchangers. We can also use the concept of stream split that you discussed in hand exchanger networks, where we again try to divide the load of the stream, and then again change the temperatures available, and as such we can actually change the area of this heat exchanger required for a particular heat transfer. So just to summarize that in this lecture we talked about several different process targets. We talked about energy targets, area targets, number of shell targets, and number of units targets. And we said that these energy and capital cost targets can be defined prior to the detailed design of the process. And actually, these targets are very important when we are selecting an optimal hand design or we are looking at an optimal value of delta T minimum. Okay, because we will select a hand design or a delta T minimum value that actually satisfy all these targets. We also talked about energy and capital cost trade-off, and we said that the energy and capital cost are not complementary to each other. If we are trying to save on energy in terms of utility cost, we might have to use high area heat exchangers. And if we are trying to actually reduce the cost of area of heat exchangers, we might have to use more external utilities. So there is always a trade-off between these two values, and then based on our process requirements and our energy requirements, we choose an optimal value of delta T. We also discussed that there might be situations where we are actually deliberately not designing an MER hand system. It means that our energy requirement would be higher compared to an MER system. And the reason being because we are trying to reduce the area or the capital cost of our system. And how we can actually optimize this suboptimal hand system so is to look at degrees of freedom in terms of shift of heat duties between different units involved in the system, the loops or utility pathways, and splitting streams. And by doing all these, we are actually trying to reduce the area of the heat exchanger network for our overall design. So that is all for this lecture. Thank you for your time.